Swayam Prabha. Digital India. Educated India.
Welcome to this lecture series on mineral resources. Mineral resources are essential for the economic development of any country. Take the case of the developed countries like United States, Canada, Australia and so on. These countries, the initial phase of their economic development largely was contributed by their mineral resources, which they exploited for the development of their industry. In the Indian context, the scenario is not that very distinct as regards to the role of mineral resources in the initial phase of development of the economy, and still we lack resources of many of the important metals like the precious metals, base metals and critical metals for energy resources, and we have to largely depend on import of these metals from other countries. So, there is a need for the augmentation of the available mineral resources and for better economic development and industrial growth. So, this course is essentially a first level undergraduate level course and is taught in many universities and institutes by different course names as economic geology or geology. And in this course we will, in this lecture series, it will be more conceptual, but not involving much of mathematics. What all little mathematics we will have towards the later part, only high school level mathematical knowledge and capabilities would be sufficient. And so, let us have a brief idea. So, the concepts and facts, figures that will be discussed here have been taken from available textbooks, like the book by Jensen, M.L. Jensen and Bateman, and by Anthony M. Evans, Lawrence Robb, Introduction to Ore Forming Process, and the book by Craig Vaughan and Skinner, Resources of the Earth, Mineral Resources, Economics and Environment by Stephen Kessler, and Ore Deposit Geology by John Ridley, and Understanding Mineral Deposit by K.C. Mishra. Although we will use various other resources and other materials, and we will be indicating them in the due course of the lecture series. So, let us have an overview. So, this course is the objective of this course is to give an overview of the subject, and the very first aspect of mineral resources is the geology. So, it is basically the science of mineral deposit formation and trying to answer very fundamental queries as to how these mineral resources formed, where they formed, when they formed, and trying to understand the rationale behind availability or distribution of these mineral resources across different continents. And once we are equipped with the scientific knowledge about the mineral resources and their formation, this can be very effectively utilized for exploration of these mineral resources in areas where they are not known to be existing as of now. Another important aspect of mineral resources involves their exploitation, use of technology and different methods, scientific methods for exploitation of these mineral resources once they are discovered. Since this does not fall in the purview of geology, this is rather the activities of the mining are done by the mining engineers. So, we will not be covering much from this aspect. Then we will see these mineral resources are essentially economic commodities. We have to see how effective policies should be formulated for their exploitation in a sustainable manner, and we need to formulate proper policies for their exploitation and to sustain for the future. Mineral resources exploitation also does affect the environment in many ways, starting from the time that they are being explored, and once they are discovered, the exploitation process, the several downstream process of extraction of these metals, the various ways that the exploitation and the extraction process, downstream industrial process involving the minerals and metals, they affect the environment, the ecology, and we have to see as to how such type of effects could be at least evaluated, and whether there are remedial measures which can be taken for the deleterious environmental impact, and that also is a responsibility. And so, these are the 4 aspects that we plan to cover in this lecture series. As we all know, we can define minerals as inorganic crystalline solids. So, minerals could be, they do occur in nature, but they can also be synthesized in laboratory. So, the missing of the term natural is intentional here. We can take them as inorganic crystalline solids. They are the minerals of different metals, as we will see the classification. So, resource is an economic term. This is essential for economic development, as I have already discussed. So, now we can say that minerals which are either direct raw materials for various industries, we know what the industries are: the ferroalloys industry, the infrastructure industry, the electrical and electronic industry, transportation industry, aviation industry, refractory, fertilizer, and so on and so forth. So, all industries either directly or indirectly depend on mineral resources as either direct raw material for them, or after the metals are extracted from the minerals, they are used in different industries. So, when these two are combined, minerals which are direct raw materials for various industries and those containing elements or metals of high economic value are our mineral resources, which we will be discussing in this lecture series. We all know why metals are so much sought after. The metals, for example, the transition metals, the precious metals like gold, platinum group of metals, platinum, palladium, osmium, iridium, and many of the metals like tin, titanium, vanadium, and so on. These metals have got very special properties. Their bulk electrical, their electrical conductivity, thermal conductivity, malleability, ductility, and so many other properties which make them very special and suited for many industries, many of our products for the modern technology, and that is the reason why these metals are so much sought after. But also the non-metals, the non-metallic minerals are also equally important, as we will be seeing them. So, we can divide the mineral kingdom broadly into 2 categories: the silicates. Silicates are the common rock forming minerals making up the bulk of the crust, of the earth's crust. Often they are used as raw materials for industries such as the glass, ceramic, refractory industry, and they are constituted of the SiO4 fundamental tetrahedral building blocks, which combine in many different proportions to give the range of silicates as you have already studied in your elementary level courses, the nesosilicate, sorosilicate, inosilicates, phyllosilicates, tectosilicate and so on. Some of the minerals like silica, SiO2 is a raw material for glass industry, and many of the clays are raw material for ceramic industry. The aluminosilicate, kyanite, sillimanite and andesite are raw materials for refractory industry and so on, and we know that they are economically important, even though they may not be as very economically valuable as the metals. The non-silicates, they mostly constitute the mineral resources as we see them here. The oxides are the hydroxides, metals like aluminum, iron, titanium, chromium, manganese, tin and uranium, and they are either the primary minerals forming in different environments, or sometimes the product of oxidation of this kind of mineral bodies when they are exposed to the surface. And metals like aluminum, iron, titanium, the bulk of the ore minerals are the oxide minerals. The carbonates, no much of metal carbonates are important as mineral resources, but it also sometimes the primary ore minerals get oxidized in the surface in the presence of carbon dioxide to give the carbonates. Some of them like the calcium carbonate, which is which constitutes the limestone, is an important raw material for cement industry. The sulfides, these constitute the most important class of the ore minerals, which we will see in a short while. Most of the transition metals and some of the other base metals and the semi metals, they do form their sulfide, their minerals which are sulfides when they constitute the resource. The halides, as we all know them, the rock salt. So phosphates, mainly thorium and the rare earth elements are available in the form of phosphates, and apatite being one of the minerals which is an important material for our fertilizer industry, and we also do look for such kind of minerals. Tungstates, it's the sole mineral for tungsten, and also the native metals. For example, the noble metals like gold and platinum, they do occur in their native form, and metals like copper also is available sometime in its native form under some special conditions. And as far as the non metals are concerned, sulfur, which is an important resource for fertilizer as well as for many medicinal purposes, and carbon, which is essentially when it is present as a gemstone is diamond. So these are some of the examples of native metals. Now these minerals, their immediate implication that you can see from here is that whenever such kind of minerals are forming under any kind of an environment, they do indicate some of the physicochemical parameters of the environment in which they are forming. For example, for the oxides to form, we need to have an environment where the oxidation state should be favorable, or to have appropriate partial pressure of carbon dioxide to form the carbonates. And sometimes we find that these minerals, as we will be discussing the attributes of the mineral resources, mineralogy of the mineral resources constitute a very important aspect. This is one of the very fundamental contribution to science. This is periodic table of elements, which guides us in understanding the many of the phenomena, chemical phenomena anywhere. And since we are interested, or the focus of our subject is mineral resources, in formation of these mineral deposits, we can always get some insight by looking at the periodic classification of elements. Here this periodic table has been taken from the book of Stephen Kessler, where you see the elements are differently shaded. The non ferrous metals, here the the elements for fertilizer, sodium, potassium, calcium, nitrogen of course is coming from the atmosphere, phosphorus and sulfur. Here are the semi metals, arsenic, antimony and bismuth, the metals like tin and lead, germanium, tin and lead, this coinage group of metal, copper, silver, gold, the platinum group of metals, the transition metals and the rare earths. Some even though we can always go on studying it to as minute details as possible, but to be brief, say for example a metal like chromium, it is very rigidly, it occurs in only +3 oxidation state in the primary rock forming cycle, although +6 is also, chromium also forms at +6 in different specific surface environment. So that's the and this metal chromium occurs is very restricted in its occurrence, in its type of, because it forms only one ore mineral, that is chromite, and it also does form a very restricted type of mineral resource. Metals like manganese occurs in a variable oxidation state from +2 to +7, but it generally occurs at its oxides, and in mineral resources it is the manganese oxides which is recovered as the ore mineral. Metals like iron has equal affinity for sulfur as well as oxygen, so it occurs as pyrite, which is the major sulfide mineral of iron, which is iron sulfide pyrite, and also as oxide, which constitutes the major bulk of the ore. The metals like zinc, cadmium, mercury, copper and the semi metals, arsenic, antimony and bismuth are essentially, they form their sulfides. Amongst the high field strength elements like titanium, vanadium, zirconium, yttrium, hafnium, tantalum, they form their oxides, in exception to molybdenum, which forms its sulfide. And these the first series rare earth elements, the lanthanides, they form in the common rock forming minerals or as phosphate, and are important resource of, they have very interesting alloying property for which they are very much sought after for improving the magnetic field, the magnetic properties of alloys. They are very much used, very much sought after. And the classification, like say for example carbon is both a source for energy as well as for precious gems, as we know it occurs as diamond, and so on. And the fertilizer industry, construction industry, these elements which we can see from the classification here. Elements of the periodic table in context of mineral resources also are geochemically classified to lithophile, siderophile, chalcophile and atmophile. The lithophile elements they generally have the tendency to get enriched in the earth's crust or formation in the rock forming silicates. They do constitute many of the large ion lithophile elements like lithium, potassium, rubidium, cesium and so on. The siderophile metals are the ones which have the maximum, they have the affinity for iron, which is marked over here in blue. They are the siderophile elements. The implication is that during the fractionation of the bulk earth to core and mantle, when the most of the iron and nickel went to the core, many of the siderophile elements like the platinum group of metals and gold also were partitioned or fractionated into the earth's core, and that's how their availability in the mantle was greatly reduced. And as shown in the previous figure from the periodic table, you could see the chalcophile metals. So these are the ones which occur as their sulfide minerals and recovered as from nature in the form of their sulfides. Atmophiles are the noble gases, which we don't consider them in the present scenario. So, these geochemical classification of elements help us in getting the first hand information about the mineral resources, what type of minerals to expect and what kind of geological environment. This diagram has been taken from the geochemical earth reference model database. Here on the x axis the abundance, the atomic number are plotted from 1 to just above 90 up to uranium, and on the y axis the abundance of these elements in reference to silicon per 10 to the power 6 atoms of silicon have been plotted. This the zigzag pattern in the abundance of these metals is a very fundamental principle that odd atomic number elements are less abundance than the even atomic number elements, and the ones which are the most abundant elements, the rock forming elements, are shown over here. The rarest metals, ruthenium, rhodium, palladium, gold, platinum, as we saw in the previous diagram, are the rarest minerals. The blue ones are the rare earth metals, which are our which occur in much trace amount compared to the other metals, and because these are on the log scale. Now, as far as the mineral resources are concerned, the fundamental questions that we ask, that in what quantity we actually get them, and if this diagram here is, it shows the relationship. On the x axis we have the log abundance on the bulk earth bulk continental crust, where the order of about 9 order of magnitude variation, means 10 to the power of minus 8 to nearly 10, where you could see the abundant metals like aluminum and iron having abundances almost as 5%, 8%, 5 to 6% in the continental crust. And on the y axis the quantity of these metals available as mineral resources in terms of metric tons, and 1 ton is 1000 kg, are plotted here. That is also on the log scale. We also see that they vary almost of the under similar about 8 or 9 orders of magnitude in the quantity of these metals, starting from very scarce metal like uranium to going up to aluminum and iron, which are available in billions of tons of such resources taken all together. They are occurring in the earth. So, this diagram gives us a very first insight that the total quantity of any particular metal that is available as a resource has some kind of a relationship, direct relationship with their abundance in the continental crust. And the diagram onto the left is a vertical scale where where a term that is written here as enrichment factor, which is mentioned here, and the metals of interest are plotted on this, or are shown on this vertical scale starting from 1 to 100,000. We see abundant metals like aluminum and iron have enrichment factor values which are less than 10, we can say that less than 1 order of magnitude. What does it tell us? It tells us that an abundant metal like aluminum and iron only needs to be very little enriched to give its to be available as a resource which you can exploit, and very scarce metal like mercury, whose crustal abundance is of the order of 10 to the power of minus 5 in weight percent, would require almost about 80,000 or more enrichment, times of 80,000 or more times enriched, so that it will be available to us in the form of a resource. It does give us some few more insights, that the processes. So that means if we when we will be looking at the different earth processes, that is what we basically try to correlate here, the all the earth processes to formation of mineral deposits. Then we see that the this scarce metals like mercury possibly would be needing multiple steps or multiple stages of enrichment so as to reach to a level where we can call them a resource, and the metals in between fall. They do also tell us, at least at the first end, that these metals will definitely take longer time to be available as resources in the earth. Now let me tell you that when we use the word resource, it is a much generalized qualitative term giving representing the total for any particular metal or mineral. What actually it comprises is the mineral or the ore deposits. These are discrete entities present that we see them and measurable in their quantity. They do satisfy some quality and quantity parameter, and the question is that where actually do we find them. So the answer is that we find them in the earth's crust, or to be more specific, in the upper crust. So what are the crustal domains in which we these ore deposits, these mineral resources, they occur in the crust, more specifically in the upper continental crust, either exposed on the surface or even going to depths as high as 5 kilometer. Quickly we can see what are the different crustal domains that we can expect to see such mineral deposits occurring. They will be occurring in recent or ancient sedimentary basins. They may be occurring in associated with magmatic bodies, subsurface intrusive magmatic bodies, in crustal scale brittle ductile deformation zones. It could be crustal scale as well as local scale deformation zones such as shear zones, fracture zones, folded strata, and so on. And these sedimentary basin also could be the marine sedimentary basins or the fluvial and so on. So we will see them, the whole spectrum, in the due course of this lecture, and let us try to look at some of the basic terminologies. What do you mean by these mineral deposits that we are talking about is essentially constituting of some entity which we can call as an ore. So we define the ore as a natural aggregate. Ore is essentially a rock. It constitutes of natural aggregate of minerals, and the only specialty is that in the ore there is the concentration of either one or more than one element is above a threshold or a background value, which is called as a Clark value after the famous geochemist F.W. Clark. It's kind of an average value concentration in the crustal rocks. So these are examples of ore This is taken from the iron ore. This is one of the photographs from the Hamersley Basin in Australia, where you could see the darker bands constituting of hematite, and the lighter bands, the red bands are the cryptocrystalline ferruginous silica known as chert. And in this, we all know that this black this gray band, which is the iron oxide, is the material of our interest, and we call that, if that is the ore mineral, then the part which we would like to discard is the gangue mineral. This is a specimen of ore from Malanchkhand copper deposit in central India, where you could see these as the sulfide minerals of copper in a matrix of quartz, and here this quartz is the gangue mineral and these are the ore minerals. And in order for this material to be qualified to be called as an ore, here we know that this concentration of metal like copper has to be above a certain value, say for example at least about 0.45% of copper to be, for this material to be called as an ore. So this ore, when we call that an ore, comes from something which is an entity occurring in association with common rocks in the crust, which is an ore body. This is an example of the ore body of copper from Malanchkhand copper mine in central India, where you could see it's a rich mineralization of copper sulfide, this copper iron sulfide chalcopyrite mineralization in this ore body. So the ore body needs to be present in a required dimension, length, breadth and width, and so that it gives us certain quantity of the metal for that to be feasible to be recovered by using our process different scientific methods for extraction of the recovery of this particular metal. So this is the example. So when we see this is a typical look of a mine where an ore body is being exploited. This is taken from the Malanchkhand mine, and if we want to represent the ore body in space, we can only do it on a geological map. So it's very important that if we want to understand the ore deposit formation processes, we do have to look at their maps at all scales. This is a mine scale geological map where the ore body, which is basically the copper rich ore body extending for a length of almost like 1.8 to 2 kilometer in surrounding rocks in association, as I told you that they occur in association with common crustal rocks. This is what is an example of a mine scale geological map. If we take a subsurface section of this ore body, we do see that it does extend to depths. That's what exactly what I mentioned, that this occurrence sometimes they are exposed or they do extend to a great depths in the subsurface, variable depths. And when such ore deposit, they can either occur independently in one geological terrain, or there could be lots of such deposit occurring together. This is the one example. This is from the Noamunde basin in Singhbhum Craton. In this particular basin itself, we get a good number of localities where the iron ore is being mined. In addition to that, there are many manganese, there are localities where the manganese ore is also being mined. This is an example where, and this is an example of a place where there are several such ore bodies can occur in a small area of just about a square kilometer, which is coming from the Ekati diamond mine in Canada, and several such. So in those cases we call them as ore district or mineral province or mineral belt or metallogenic province. There are many such examples of such kind of metallogenic province. The classic examples come from the Abitibi greenstone belt in Canada, Kalgoorlie gold district in Iligan-Craton in Western Australia, Carlin Trent in Nevada, United States of America, where it's a very rich zone producing gold ores, and the gold bearing schist belts in Thorwald Craton. These are some of the examples of the metallogenic province or mineral belts. So we will continue discussing about these mineral resources in the subsequent classes. Thank you.